And welcome everybody to this special talking about unified theories here, or the theory of everything, speaking with theoretical physicist Eugene Bagashov. And today we'll talk about the theory of everything. And by that I mean general relativity versus quantum field theory. So Eugene, we spoke in detail yesterday about the various different theories about everything, and there are many different terms involved. We want this to be kind of a basic, sort of a mainstream explanation of the differences between quantum field theory and general relativity. And part of our now forming nonprofit organization is to assist, study, and report on the ongoing formation of a unified theory of physics. And while this may not be possible or even useful, we'd like our donors, viewers, and colleagues to have an understanding of what we mean by a unified theory of physics. So, hi, Eugene, thanks for taking a moment to talk about the theories of everything. Yesterday, we spent considerable time talking about fields, waves, and particles.
Yeah, hello.
Hey.
Thank you for having me.
Yeah, thanks for being.
Yeah, we've had quite a long discussion. So unfortunately, it wasn't recorded, but.
Well, that's okay. I think we needed more organization than we had. We were just kind of just spitballing everything and kind of seeing where each other were in terms of being on the same page to what we were talking about. As it gets a little bit to the point where you're wondering what you're measuring at some point when you start to talk about this stuff. So
yeah, I imagine today we're gonna ramble also a little bit, but hopefully we'll have a bit more structure.
Yeah. So first, would you like to provide a brief explanation of the work of previous scientists that led to Einstein's general relativity?
Okay, so, well, I would say there weren't many scientists before Einstein in the sense that Newtonian gravitation, well, it's basically works of Newton and Kepler and Hooke and people like that. So Newtonian gravitation was already established in like late 1600s. It was already known by then, and it was the dominant theory, especially in the 18th and 19th century. But the discovery of special relativity, or rather, I shouldn't say discovery, but development probably is a better word, in early 1900s, it required, let's say, certain enhancements to Newtonian gravitation. So certain people like Hilbert and Einstein, first and foremost, developed these new equations, which are now called Einstein's equations or Hilbert-Einstein's equations. They're basically developed simultaneously by Hilbert and Einstein. So it's not only Einstein who did those kinds of things. So these equations are the main thing in general relativity, kind of like Newton's laws of motion for Newtonian physics or Newton's law of gravitation.
Okay.
So in these equations, we have on the left side basically gravitation, which is described by a special mathematical object called a tensor. And basically special relativity and general relativity is mostly formulated in terms of these objects. So a tensor is basically a generalization of a concept of vector. It's like a lot of vectors packed in a single entity. Basically, that's what a tensor is. So on the left side of these equations of general relativity, we have a tensor of gravitational field. And on the right side, we have a tensor of basically matter. So all the other kinds of fields, like electromagnetic field, for example.
Okay.
So so the idea is basically that the matter kind of produces the gravitation. The matter on the right side produces the gravitation on the left side. But at the same time, and this is, by the way, one of the problems of general relativity, is that the gravitation on the left side simultaneously affects the matter on the right side, right? So it's kind of, it goes both ways, and technically it's called nonlinear equations. So they're not that easy to solve because you need to adjust the left side to the right side simultaneously. Whereas like you like adjust the left side a little bit and your right side immediately changes. So, so that's why the solutions to these equations are very hard to find.
Sure.
So you probably heard of some of the solutions, like Schwarzschild solution for
sure, yeah.
Spherical, just basically what's a single spherical body I mean, according to these equations, would produce gravitation.
Like a black hole
as
event horizon would be an example there.
Yeah, it's a very classical example with the black hole Schwarzschild solution. So it was discovered in, I think, 1914 or something like that, or maybe 1918. But the next solution, which also took into account rotation of this object, was only discovered in 1960s. So it took like half a century. It's called the Kerr solution. But then also electric charge was added, etc. So it's a very hard thing to work with. That's basically my point.
Okay, right. General relativity is tough to work with.
Yeah, exactly. And so one of the main ideas, I guess, is that, and this is, by the way, only an interpretation, which was used by both Hilbert and Einstein. It's the geometrical interpretation of these equations. So what they say is that let us get rid of forces, basically. So we get rid of all the dynamics, and we just replace it with the curvature of space-time, right? So all the particles, all the bodies would be moving inertially, but on the background of this curved space-time. So no forces exist there, no like dynamics or anything like that. It's just inertial motion on the curved space-time, basically. That's what it is. And so all the fields of matter, they curve space-time instead of acting as forces, as in regular physics, let's say, pre-general relativity physics.
Okay.
But this is, and I repeat, this is only an interpretation. You may construct a general relativity on a flat space-time, what is called flat, but it's meant in 3 dimensions, flat, in the sense that not curved. So you may construct general relativity in a flat space-time with forces and dynamics and fields, but this is usually not being done. But it might be a more fruitful approach, and some scientists have worked on this.
Okay.
Yeah, but this is usually ignored in sort of mainstream kind of world.
All right, so I think you've basically covered the first and second questions that we have there, whereas you briefly described general relativity, mass warping space-time, and so on. Kind of that's the basics of Einstein's general relativity, right?
More or less, yeah.
Okay, so let's talk briefly about quantum field theory, which is again the main theory of everything alongside general relativity.
Yeah, so in quantum field theory, and it is indeed considered like the most fundamental theory today because it describes, supposedly describes all the particles, etc. So what it deals with fundamentally are fields, exactly that. And you might imagine a field as a medium, like an ocean or something, or an atmosphere. Well, ocean would probably be easier. So it exists everywhere. All kinds of fields exist everywhere. It's just that for the most part, they exist in what is called a vacuum state. So a vacuum is not an emptiness, according to quantum field theory. It is a main state of quantum fields. And by quantum fields, I mean all kinds of fields, like electromagnetic field, electron field, quark fields, gluon fields, etc., etc. But so the vacuum state is the main state, like the lowest energy state. But if you provide a certain energy to a field, it becomes excited, and a particle is born. So according to quantum field theory, a particle is an excitation of a field. You may represent this as sort of like a wave traveling on top of the ocean. So the ocean is the field and the wave is the excitation of this field. And it may propagate, it may interact with other particles, which are also, excitations of fields, etc. So this is how quantum field theory perceives the world, more or less.
Yeah, and by the way, for our viewers, Eugene did a pretty long presentation about quantum mechanics on his channel. We'll link that below the video, I think, here. That's still up on your channel, right, Eugene?
It's not my channel, but yeah, but it's there.
Okay, all right.
Hopefully, at least, if it wasn't proven.
All right, it's probably still there, but it was a great primer similar to the one you just did, but just a little bit more in depth and with visual aids, I think, if I remember correctly, about quantum
Yeah,
mechanics.
there's a pretty big presentation there. I mean, a lot of slides. But it's about quantum mechanics, which isn't quite the same as quantum field theory. So, but
Oh, okay.
the differences may be quite hard to explain. So basically, quantum field theory deals with a lot of particles. This is the main difference. Whereas quantum mechanics deals with like one particle or two particles, you know.
Right, right, right.
But in quantum field theory, we're dealing with like lots of particles simultaneously. So the mathematical description of quantum mechanics and quantum field theory differs mostly because of that.
And so, just a brief aside. There are some benefits to looking at parts of the universe through the lens of relativity versus aspects of looking through parts of the universe in terms of quantum field theory, correct?
Yeah, well, quantum field theory actually is mostly applied to particle physics. So that's
Sure.
like, you know,
The subatomic
accelerator
world.
physics.
Yeah.
Although in astrophysics, you also have high energy processes, which, well, even, you know, like cosmic ray physics, there's all kinds of particle processes involved, like nuclear reactions, production of antimatter and things like that.
Right, right.
In those showers of charged particles that we get when, let's say, a cosmic ray proton, high energy proton impacts our atmosphere. But mostly for macroscopic bodies, indeed, the general relativity is sort of like the way to go. But at the same time, you should also keep in mind that general relativity is not used, for example, in many other applications. Like when people describe rotations of galaxies, you know, the famous dark matter problem and
Sure,
things like
sure.
that, it's not general relativity. People just use Newtonian dynamics. So general relativity is supposed to be needed when you have strong gravitational fields. And you might say, well, a galaxy has a strong gravitational field, but this is not the case. I mean, if you look at, if you calculate the forces that act on stars from gravitation, I mean, from galaxy, they are very small forces. If you calculate the accelerations, they're just super small.
And that's largely because of the distance and the distance at which
Yes,
gravity is able to impart forces upon things.
exactly. It's mostly because of distance. So, I mean, if the sun orbits the galaxy at like 50 or something like that, 50,000 light years away from the center, or maybe 30, I don't
Something
exactly know,
something
but
like that. But yeah,
yes.
on
So,
that
but
scale.
this is a very long distance. So the gravitational acceleration towards the center is very small, very, very, very small. Uh,
Right.
so people use Newtonian physics here.
And there's all kinds of different ways that the movement of these objects is measured. Close objects can be measured by parallax, and farther away objects. And relativity brings up all kinds of issues with how things like galaxies rotate without flying apart, which is how the dark matter and dark energy, well, at least the dark matter part. And then, of course, you got the acceleration of the galaxies. We don't want to get too in depth into that because, but yeah. So, all right, good, perfect. Anything else about quantum field theory? At
Well,
least
there's
in
a
this
lot.
basic, at least in this basic primer kind of format that we're doing here.
Mm-hmm. Well, I don't think so. I'm more or less covered the basics. Although we might talk about the problems, let's say, of quantum field theory or general relativity, if you like.
Yeah, but one thing before that, would you mind translating or explaining this image that you sent yesterday, the one that you translated from Cyrillic Russian?
Yeah, okay. So this image shows more or less the relationship between different theories. So we have these three axes where like the axis that goes to the left, sort of bottom left, is the axis of the speed of light. Well, it's actually inverse speed of light, which means kind of how big is your velocity relative to the speed of light. And then the axis that goes to the right is the gravitational constant, this gamma n, which means like Newtonian gravitational constant. It just shows you how big of a gravitational field you have. And then the axis that goes to the top is the h, which is the Planck's constant, which is the main constant of quantum physics. So basically, this graph shows different theories and how they relate to these constants and each other. So, for example, on the axis of C, we have special relativity, which works with, again, phenomena that describe the motions of bodies with large velocities.
Right.
Then on the axis of gamma, this gravitational constant, we have gravitation in Newton-Cartan space, which basically is also a geometrical reformulation, I guess, of Newtonian
physics. Right.
Yeah, so it's kind of in between general relativity and Newtonian Newtonian gravitation, I guess.
Yeah.
So yeah, then at the bottom edge, so the one that kind of covers simultaneously the C and gamma, we have general relativity, which is, again, it kind of covers both the large velocities and large gravitational fields.
I see. And now when
that's why it's in between. Yeah.
Perfect. It's finally you finally caused all the dots to be connected for me, and for that I thank you. So that when we're looking at this top vector, we're talking about the subatomic world.
Yes.
Perfect. Thank you very much, because I finally get it now.
Yeah, so on the top axis, we have non-relativistic quantum mechanics that is lying on the axis itself. So it's just regular quantum mechanics. So it deals with very small bodies, very small processes in terms of size, in terms of energy, etc. So it's a very typical quantum mechanical problems, like let's say electron in an atom or something like that. And then in between that and C axis, we have the edge, which is the quantum field theory. Here it says that it's Minkowski space. Well, what is Minkowski space? It's basically a flat space-time. So it's a four-dimensional, kind of Euclidean space. Although
length, width, depth, and time, right? Length, width, depth, and time.
Yes, exactly. So quantum field theory, the one we've talked about, the theory that describes particles and fields, it's formulated in this flat space-time. So, and this is, by the way, one of the problems why it's hard to reconcile with general relativity, because it's formulated in curved space-time.
Right, and that gravity has to warp space-time. So if you've got you're comparing a 2D universe versus a 3D universe, essentially.
Well, in some analogy, you might say that, yeah.
Or maybe a 2D universe versus a 4D universe, I suppose, would be more accurate.
Kind of, yeah. So there is a problem in this respect. Then between H and gamma, we have an edge which is described by non-relativistic quantum theory in Newton-Cartan space, which is, again, sort of like a generalization of quantum mechanics on these curved space-time, but it has its own problems. I mean, it's not very well developed theory. Again, for the reasons I've already mentioned.
I see.
And finally, kind of the edge that unifies everything, the one that lies towards us, is this relativistic quantum theory, and part of it, this shaded part, is quantum mechanics in an external gravitational field. So this one, quantum mechanics in an external gravitational field, might be solved more or less successfully, and it has been done in like 1980s. But and by the way, this book is the book I took this picture from is exactly about that. But relativistic quantum theory has not been built yet, and there are doubts that it can be built. So the theory that would unify all those three things, so strong gravitational fields, large velocities, and quantum phenomena, it's not there, at least yet.
Okay, got it. That sounds like about what I'm thinking about here. Thank you, thank you for putting it into terms that make sense. Because, well, let's just say I know what goes into PhD programs.
Was that a joke?
No, well, my best friend is actually a PhD in biology. So it's some kind of a specialized aspect of biology, and I know how exhaustive his processes were in order to make it through that process at USC. So I while I'm not in college or anything like that myself, I totally understand the complexity of the situation you're exposed to here.
Well, I'm not sure about biologists, but I know that medics are famous for having, really tough time.
Yeah, that's true.
Studying.
Yeah, I mean, he, my friend Sam, he's had to spend a lot of time regarding organic chemistry. Let's just say. I guess I can't really tell you too much about what he's doing because some of it is actually proprietary. But anyway, shout out Sam if you're watching the video. All right, so let's see. Have we discussed the problems with? I think we've discussed the problems with general relativity and quantum field theory. What?
Well, more or less, I would just like to add something that some people do not realize is that in general relativity there is a problem with conservation of energy, the conservation of momentum. So strictly speaking, it's not there.
Okay.
Just plainly put. So, and that's because in special relativity, so that's just the theory with large velocities, but without gravitational, essentially. So in special relativity, you can formulate the conservation of energy and momentum and things like that, and it would be okay. But in general relativity, especially in this interpretation, geometric interpretation of it, your, again, tensor, this special object, energy momentum tensor, does not contain gravitational energy. Because again, this tensor of matter, so to speak, it sits in the right side, whereas gravitation sits on the left side of the equation. And so there are different things. So since the energy momentum tensor does not contain gravitation in it, you cannot claim that your energy is conserved, because what is conserved is everything else except gravitation.
It's kind of like a violation of Newton's second law there, action and reaction, right?
Well, that's the third law, actually.
But, okay, third law, right?
And yeah, in some sense, probably, yeah.
Right.
But so the general point I'm making is that the conservation of energy and momentum is not present, strictly speaking, in general relativity. And that's a big problem. And again, another big problem is that all the other theories essentially are formulated in flat spacetime, whereas general relativity is formulated with this curved spacetime. Although, as I've said, you might reformulate it in a flat space-time also, but people don't do that for some reason. Again, following Einstein and Hilbert. Okay. And with quantum field theory, well, there are many problems regarding the complexity of the theory itself. I mean, people try to again come up with some unifying principles, etc., because, well, you've probably heard about how many particles we have, how many interactions we have. Like there are 4 fundamental interactions, like weak, strong, gravitational, and electromagnetic. But we also have 5th interaction now, which is Higgs interaction, and etc., etc. So it's very complex, and people have only been able to unify the electromagnetic and weak interaction. So it was pretty successful, but with strong interaction, there are a lot of problems. There is a problem. It's actually the field where I'm working in, so I'm fairly familiar with it. There is a problem of confinement of quarks and gluons. So supposedly, let's say proton consists of quarks and gluons. So a proton is 3 quarks plus a lot of gluons, etc. And well, it's quite complicated. But anyway, the point is that we cannot observe these quarks. We can only observe, let's say, protons and neutrons and other particles that are made of quarks, but we don't observe quarks. And that's a big problem, you see.
Yeah, and
So
when you've got waves interacting with waves interacting with waves interacting with waves, you get a lot of interference. Last time I checked, right?
yeah, so basically what I'm saying is that, and plus there is a lot of, like technical mathematical problems. There is a lot of unexplained phenomena in purely technical terms. Like you need what is called renormalization. Maybe you've heard about that. It's also a big problem because when you make calculations according to principles of quantum field theory, you often encounter infinities. And what
Uh-huh.
people do, what people do is remove these infinities just manually, basically, just subtracting them. And this procedure is called renormalization. And it's very suspicious, and people have been
Sounds it.
struggling with it
Yeah.
for like half a century at the very least, or maybe more, like since 1950s.
Is this a segue into why you don't like cosmology because of things called black holes, or is it just my
Uh,
imagination?
well, speaking about black holes, this is basically an artifact of general relativity.
Right. Exactly. Exactly.
It's a mathematical artifact. It's nothing more than that.
All right. So let me
Uh,
let me let me interrupt you. What are the most important areas of study that will advance physics?
hmm, well, I have sort of like a philosophical approach to things,
By
and
all means.
so yeah, so I would say that you need to seriously revisit logic, thermodynamics, and statistics.
I agree.
Those three things are the key to solving, or rather untangling many problems that we have today in many areas of physics. And
All
not
right.
only physics, I mean, many related areas like, again, climatology or whatever, things like that.
I think we may have to revisit what you said there at a later time about thermodynamics, as that's a very interesting topic and here's a segue to the next question in cosmology. Why don't you like cosmology, Eugene? I think I know why, but I'm intrigued nonetheless.
Well, it's mostly because,
Is it because of all the
well,
fiction and assumptions and upon assumptions upon assumptions?
yes, because
Got it.
the experiments are basically impossible, and the observations may be interpreted in like many different ways.
Right, right, right.
So,
I agree.
and you might, and again, people invent all kinds of stupid things like dark energy and dark matter, and like I just dislike that. Like it's just such a dirty, area that once you go into there, you become dirty yourself. So
Well,
just
I hear you.
stay away from it.
Doesn't it seem like a great science that can be fixed up a lot though with maybe some further understanding of things like, I don't know, the way the sun works or something like that?
Yeah, it certainly can be enhanced. And again, like these new developments, or relatively new, let's say, in understanding of cosmic plasmas, definitely help cosmology out. Like if you read Alfvén's Cosmic Plasma, the book from 1981, and by the way, I've recently made a synopsis of this book, so I can give you the link that you can share.
Yeah, that's cool.
Uh,
We'll leave it under the video. I'd like to read it
yeah,
myself.
okay.
I
So
could
in
use a
this book,
refresher.
so in this book, Alfvén describes how new understanding of plasmas might seriously impact cosmology. Like again, there's problem with quasars. Well, Alfvén, this Hals and Arp's work, where he shows that high redshifted quasars are often associated with low redshift galaxies, which is very strange, et cetera, et cetera. So, well, Alfvén actually considers quasars as being what he calls an ambi-star, where, well, basically his idea is that in the universe, matter and antimatter should be balanced. And it is so-called Alfvén-Klein cosmology.
Oh, I'm familiar with it. But let's not get into
Yes.
the weeds on this in this video
Yeah,
because we're
I was just mentioning
all
that,
right, go on.
there are many new developments, and again, the
Oh
problem
yeah.
with, let's say, Olber's paradox, which states that the sky should be very bright because statistically speaking, you should see stars everywhere. If the universe is infinite, let's say. But it's only if the universe is homogeneous, you know. But
Sure.
again, as Alfvén points out, the universe is not homogeneous due to the behavior of plasma. Like plasma tends to form structures. So the
Absolutely.
space should have like a cellular filamentary kind of structure.
And indeed
And
it does.
in this case, Olber's paradox would be solved, and you might have infinite universe without it being super bright, you know.
Okay,
Well,
I get that.
etc. So yeah.
So if you had unlimited funding, Eugene, what would be your first epic science experiment to advance or perhaps even debunk existing theories of everything?
Hmm. Well, that's a difficult question. I don't know,
Oh, you can
really.
pass if you like. That's fine.
Uh-huh.
You can pass if you like.
Yeah, well, I just don't know how you can make experiment regarding theories of everything. Like, it just seems pretty hard. Uh, one thing, hmm, one thing that comes up on my mind, and it's a completely random thing, but I guess I'll just mention it, is
Yeah.
the recent experiments regarding gravitation of how gravitation acts on antimatter. So the problem is we don't have enough antimatter to determine if it's being attracted or repelled
Oh,
by the
wow.
Earth. Yeah, so people have been struggling with that. So I guess,
Huh.
and also one other thing I'm interested in is like various temporal changes. Like people have been noting that, let's say, if you measure gravitational constant, it fluctuates or seems to fluctuate with time. Uh, and it almost does that in like sine wave kind of pattern with 5.9 year period. So I would just,
Perhaps
do these kinds of measurements, I
perhaps
guess.
gravity has some sort of a half-life. I remember hearing about that in the late 90s. There was a theory going around that gravity perhaps has a half-life as it's some sort of a remnant feature of some sort of other perhaps unobserved cosmic behaviors or something like that. I don't remember exactly the specifics of it, but something about gravitational half-lives used to be a thing in the late 90s that people were
Mm-hmm.
considering.
I don't know. I never heard anything about that, but okay.
Anyway, is there anything else you'd like to add on the conversation about theories of everything and so on? I know it gets convoluted real quick, but
Mm-hmm.
if we don't study the
Well,
hard stuff, it's somebody's got to study the difficult stuff, right?
yeah, well, I can just repeat what I said yesterday, is that we can only hope to build a theory of everything if we base this idea on, if we are following the presupposition that the universe is like understandable, or something to that effect. Like if the universe was created by God, let's say, again, as people thought in like 17th century, even early scientists, like people like Francis Bacon, they were literally saying that the universe is created by God and by following laws of mathematics. So if we study the universe according to the laws of mathematics, we better know God, and we also know the universe
Yeah, I get
because
that.
we can, because it was created in this intellectually understandable way. But if we remove God from this picture, we have a problem because, well, there's no guarantee that we can understand the universe. So there is no guarantee that the theory of everything can be built, and et cetera, et cetera. So all kinds of problems appear here. So again, I'm pretty skeptical about the theory of everything. That's basically my conclusion.
All right, that's substantial. Is there anything you'd like to plug, like your YouTube channel, anything like that?
Yeah, well, there's a channel called Eugene the Philosopher where I discuss various philosophical questions and also sometimes, actually, most of the time, regarding science. So maybe it would be interested.
Cool.
Your viewers would be interested.
Yeah, we'll definitely link to that. I think I put one of your videos up in our daily space weather video yesterday because I was just taking a screen grab to get a graphic of you. By the way,
Okay.
it's difficult to get you when you're talking and looking at the camera. So, but I was able to
Mm-hmm.
get a frame. And anyway, anything else you'd like to add?
No, I don't think so. I think we've covered most of it.
All right, cool. Well, thanks again, Eugene, for taking the time to talk. And sharing information with our viewers and donors also. Don't hesitate to reach out, and we'd be delighted to have you back, even though you don't like cosmology.
Okay, thank you for having me, and I apologize that I've interrupted you quite a bit. So
Oh no, that's
I'm
okay.
sorry.
It's you. This was
Yeah.
designed to have you basically at the helm, and me just to sort of provide some steering feedback occasionally.
Okay, so thank you again, and thanks to your viewers and listeners.
All right, cheers. The video will be up soon, and look forward to sharing it all over the internet. Thanks again.
Okay, thank you.